Bismillahirrahmanirrahim. This is lecture 9 of Real Statistics and Islamic Approach. We will study regression models in this chapter, but we will study them from an unusual perspective. We will argue that these models are completely wrong and useless and should be discarded. To understand why this is so, we need to look at the big picture, which requires going back into the regression methodology, which we will discuss briefly. We can think of the real world as consisting of factors or variables like consumption, investment, income, and also causal effects. For example, increasing incomes would lead to increasing consumption. Only some aspects of these real world structures are observable. And even when we observe something, the numbers that we get to measure may not actually be the factor which we want to measure. For example, intelligence is a hidden factor, and the IQ test provides a number which is an indicator, but it is not the same thing as intelligence. So once we have this picture in mind, then an econometric model is a model of the observable numbers that we see. As opposed to this, a real model tries to match the real world factors and the real world causal effects. So this creates a great difference between the two types of models. So real models and econometric models have different goals. It's useful to have some notation to better understand the difference. So we'll use a star to indicate an unobservable. So F star is an unobservable factor like consumption or income. And F is the observable indicator, like what the surveyors measure, which may be different from the actual income. And we will use this equal arrow to denote causality. So now in terms of this notation, the real models that we will study would like to discover, they have the goal of discovering what are the real factors which drive the economy, like F star and G star, and what are the causal effects. Does F star cause G star or otherwise, or maybe they are two independent things and neither causes the other. These are the hidden structures of reality which we want to discover. As opposed to this, econometric models only aim to deal with the observable counterparts, the F and the G, which are measured and indicators, and we want to create a model to deal with the relationships, the observable relationships, which are correlations and not causations. So there is a dramatic difference between the goals of the two models. Conventional statistics is based on the nominalist methodology, whereas in this course the title Real Statistics indicates our preference for the realist methodology, and the difference is explained in this slide. In the nominalist methodology, which is currently dominant, we search for patterns in the data. Anyhow we can find patterns. Any pattern in the data is a candidate for a scientific law. We can confirm this if this law continues to hold, if the pattern continues beyond the data, so it's by prediction. And what does it mean to explain? It means that we have found a pattern and the new data fits into this pattern. That's called explanation. All of these four principles are rejected by the realist approach, which says that no, we search for a deeper explanation. We don't look in the data for understanding the data. We look beyond the data. We look underneath the data. We look at the real world which generated the data. So we look for entities and causal effects and laws which explain why the observations look the way they do. And the scientific laws are hypotheses about how the hidden reality works. Confirmation can be done by many, many different ways, one of which is prediction and forecasting, but this is not necessarily the best way, and sometimes this doesn't work. There are many other approaches to confirmation of hypotheses. And explanation means that if we assume that there is some hidden entity and it explains what we see, then that is called an explanation. Regression is an extension of this Fisherian methodology, or this positivist or nominalist methodology, to more complex data sets. Regression is based on a large number of false assumptions. The positivist philosophy says it doesn't matter what kind of assumptions you make. The only thing we need to do is check the fit between the model and the data. The realist philosophy which we follow says that no, if you make false assumptions, you will get false results. In the standard course, you are taught what these assumptions are and how we use them to derive the mathematical apparatus underlying the regression model. And this takes a whole semester of work, but all of this is useless because those assumptions are wrong and all the derivations that you make from them are wrong. So in this course, we will study regressions modeled from the outside, not going into the depth of what are the assumptions and what are the calculations. An essential topic which is missing from regressions and statistics is causality. So we will introduce a new notation to talk about causality, because this without considering causality, all of the discussion is meaningless. So we will use this x equals arrow y to indicate that x causes y. So this is going to be our notation, and what does this mean? It just means that changes in x lead to changes in y. And this is a direct relationship, that is, x is a direct, immediate cause of y. We can also have indirect causal relationships, x causes y, which causes y. This is not at all equivalent. In this situation, we say that w is a mediator of the relationship between x and y. It comes in the middle. When we say that x causes y, other factors may also be causing y. So x causes y and z causes y. This is also possible and often the case. Often a variable is affected by many different causal factors. In addition, you can have multiple chains of causation. X causes y and also x causes w, which also causes y. So both of these things can simultaneously hold. Typically, we will not allow for cyclical relationships, that x causes y and y also causes x. That causes certain complications. So we will generally assume that this cannot happen. But sometimes there are some special cases in which bidirectional causation is possible, and we will discuss them as exceptional special cases when necessary. Because causality is not discussed, the real assumptions of the regression model are hidden and very confusing. So we will make them explicit. An immediate assumption is that x is a cause of y. Y is the dependent variable and x is the regressor or the exogenous variable. This is often said, but nobody understands what exogenous means and what dependent means. But basically the meaning is that there is a causal relationship between x and y. So then there is also an assumption of linearity. This is a very strong assumption and causes much difficulty, but the assumption is that y is equal to ax plus some other factors. So this is a linear relationship between y and x. And so there are many other factors that we may assume, but what we do is we aggregate all of the unknown factors, the unconsidered factor, into what is called the error term. So we get y equals ax plus an error term. Then we come to assumptions which are quite incredible. So we assume that the error is independent of x. What this means is that x does not have any causal connection to the errors. Neither x causes the unknown factors nor the unknown factors cause x. So again, I have introduced a new notation which is equal / arrow to show lack of causality. So x does not cause fi and fi does not cause x. So we have data on y's for many time periods or many sections or sectors in a panel. So for there will be values of x and y and error for each of these sectors. So one of the assumptions is that the error is independent across time or across sectors. And then there's the Fisherian assumption that this error is a random sample from some common unknown distribution. Now, these are all very strong assumptions and there is no basis for them. And can we expect them to be roughly valid? In most applications, they are very far from true. There are a very few applications where the assumptions may be approximately true. Leamer introduced what he called the axiom of correct specification, and this says that if all of the assumptions are true, only then will your regression give you sound results. Of course, this is obvious, but the point is that regression is very, very, very often used without verifying the assumptions. And in fact, some of the assumptions are impossible to verify because they are about unknown, unobserved, unmeasured error terms. So the assumptions being made are quite incredible, quite bizarre. It's almost impossible to think of situations where they could hold. And so nearly all the regressions we see in the literature are run on the basis of false assumptions, and this leads to false results. And many, many examples of failure of regression models can be demonstrated. But I think the biggest problem with these assumptions is that they create immense amount of confusion in the minds of students about causality. And the students are crippled in terms of their ability to understand data and what it tells us about the world. Basically, regression is about taking a data set and fitting a straight line through that data set. And the line should approximate the data in some ways. So the question in real context is, why are we fitting a line? And so what does this line mean? And how do we calculate it? And what will we do with this regression analysis? All four of these questions are important, and the answers to them matter. In real world situations, there are many, many different uses for fitting lines, and according to the use, the methodology of how we fit the line will vary. Generally speaking, regression methodology is only one of many different possible ways of fitting lines, and typically speaking, a visual fit, just fitting a line by eye graphically, is superior to regression. Many regressions in the literature are just meaningless nonsense, but we will study one example which deals with a meaningful situation, but despite that, all of the regressions we can run are meaningless. So we would like to measure serum kanamycin levels in blood samples in a baby. Actually, what we want to do is measure the level of serum K in the blood of the body, but it is impractical to take all of the body blood and measure it. So we take a sample. We take a sample from the umbilical catheter, and we take a sample from a vein running in the heel. So these are two different methods which we can use to try to measure the serum K levels. And this is real data set taken from the internet. For 20 babies this was done, and measurements were made on both measures, on the heel stick sample and the catheter sample. And this is a plot of the two measures. And as you can see, the two numbers are running fairly close together, which is what we expect. Both of these measures are trying to measure the same quantity, the true serum K levels in the blood, which is the unknown reality. And then the samples are the observed numbers. So the question is, how does these observations relate to the underlying reality? This is a practical question about whether or not which method of measurement is better, and whether or not these two give equivalent measures. A line in the data can show us the hypothesis of equality, that both measures are equal to some extent. Regression methodology, which can be used and we will use to show, it adds nothing at all to the underlying picture. The correct model can be that the first measure from the heel is we'll use the letter K for the true serum K level in the body blood, which is unknown and unobserved. And we will say that, okay, first measure is K plus or minus some error, and the second measure, the heel measure and the catheter measure, both of them are the true value plus or minus some error. So this is a good model because it matches the underlying unobserved reality. The errors are meaningful. They have meaning. There is a true blood level, and then there is the sample from it, and the measure of the sample, how well it reflects the true medal. This is the error. And there is also a causal chain here. The true blood level is the cause of the catheter, and it is the cause of the heel, that is the serum K levels in the catheter and in the heel prick, come from and are determined by, are caused by the serum K levels in the body of the baby. We're trying to use the heel and the catheter measures to estimate the true unknown, unobserved level K of the serum K in the blood of the baby. We have no way of knowing that, but when you have two measurements, it's generally a good idea to take the average. This tends to reduce the variability and give you more precise estimates. So we can take K star as an estimate of the unknown K, the average of the heel measure and the catheter measure, and this average gives us a better estimate of K than either of the two, typically under standard assumptions. So the picture shows the graph of the data, and then the orange line is the graph of the average, and you can see that the orange lies in the middle. And also you can look at the errors. The errors is the difference between the heel and the catheter and the average of the two. So obviously the two errors cancel are positive and negative of each other because the average is in the middle. And you can see that the errors are generally lying between +2 and -2, except towards the end, the scale and the x-axis is the average. So as the average increases, you can see that there seems to be a slight increase in the errors. So if we arrange the data according to the value of K star, which is our best estimate of the actual serum K level in the baby, then the graph tells us that when you have higher serum K levels, then the errors tend to be larger. There are three errors which can be called as largest. The largest one is at the highest value of K star at 30, and that's about -3.6 and +3.6. And then there are two large errors, 2.5 and 2.65. And other than these three errors which are above 2, all errors are between plus and -2. So we can say that in 20 cases, there are three errors which are above 2, and in 85% of the cases, the errors are less than 2. So this is more or less useful data about how accurate these measurements are, how close they are to each other. And basically, this is what we can tell from this data, and there's nothing more that regression can tell us. In fact, as we will see, regression actually tells us the wrong kinds of things. So just for the sake of illustration, we will do what I have called an outside or an external analysis. This means that we don't really look at the details of what goes on inside the regression. We just look at how regression is done from the outside. So here's a comparison of the two methods. The method that we are using treats regression as a black box. So what we do is we choose a dependent variable, we choose an explanatory variable, and our goal is to explain y using x, and we just take data on these variables and feed the data to the computer. We get the regression output and we learn how to interpret the output. We don't worry about what the computer does with the data. The internal analysis, which is what all existing texts teach, is that they teach you what the assumptions are, what the mathematics is, and what the statistical analysis is. So you have to learn the assumptions and learn the statistics and learn how to estimate, and then we learn about the properties of the estimators and the tests, and then we use all of this theory to interpret the results of the regression. So I'm going to dump all of this theory in a box and just look at the numbers as they come out and explain how these are interpreted. So what we're trying to do is to measure the true blood count K by two samples, one of which is heel stick H and the other one is the catheter C. So that we have data on H and C, but we have no data on K. So if we want to do regression, regression can only be done on observables. So we either can regress H on C or C on H, but we cannot regress on K. Now neither of these two models is correct. It is not true that C is a cause of H, and it is not true that H is a cause of C. Both are commonly caused by K. Both of these regression models lead to the wrong inferences, and they are both different. So we'll just demonstrate the regression model and what it means as an illustration of how regression is done and what it means. There are lots and lots of packages for doing regressions, and I have used a package built in Excel, and this is what the output looks like. And basically the thing to look at, this is a regression of heel stick measures on the catheter measures. There's an R squared which is at the top, 83%, that's an R. R squared is 69%, which is the square of the first number. And then there is the F statistic, 40.6, and the significance of the F statistics. And then the most important things in the regression are the coefficients, which are at the bottom of the first column or the second column. And these coefficients are, the intercept is 4.21, and the catheter has a coefficient of 0.786992, which can be summarized as 0.79. And what these numbers mean we will discuss shortly. The R measures correlation and squares measure the square of it. This is a measure of association under very stringent assumptions about the data. And this number can give highly misleading results if the assumptions are violated. In this case, there is a pretty clear linear relationship, so it leads to an 83% correlation and an R squared of 69%. And these are big numbers, which means that there is a relationship between H and C. And the R squared relationship says that 69% of the variation in H can be explained by the C variable. This is what it is supposed to mean, but actually this is not very meaningful. This has no meaning. This idea, the analysis of variance, was invented by Fisher because he was pursuing racist goals. He wanted to know how much of the variation in the child's intelligence was due to genetics and how much variation was due to environmental factors. But this cannot actually be done so easily or cleanly at all. The central goal of regression is to fit a line, and this particular regression we end up fitting a line h equals 4.21 plus 0.79c plus an error. This line is plotted in this diagram, in which the c, or the catheter measurement, is the x-axis, h is the y-axis, the dependent variable. The line shows the regression line, and the blue dots are the actual data. So basically, if we look at it by eye, we see that the line is a reasonable fit to the data, and this line captures a pattern in the data, but this pattern in the data is not real. The estimates, the numbers 4.2 and 0.7, make no sense at all, because the two measures should be roughly equal. So actually the so-called true coefficient should be 0 and 1. H is equal to C plus some error. But the regression gives us the wrong results. Sort of correct regression models would be C equals A plus BK plus error and H equals E plus FK plus error, where the true coefficients in this case, when you have models which are structural, that means they reflect the structure of reality, it would be C equals 0 plus 1 times K, because the two C is actually measuring K plus some error. And again, in the H model, the true parameters would be 0 and 1. But these regressions cannot be run because we have no observations on K, and positivist philosophy says that if you can't observe something, then you shouldn't use any models based on that. So if we close our eyes to the unobserved reality, then we have only possibilities of C on H or H on C. K is not there, and K cannot be used. Finally, we discussed the significance level of the F statistic. So basically, assume a coin is fair, and we flip it and we see 70 heads. What is the possibility of seeing 70 heads? The p-value measures the chance of the observed outcome plus all more extreme outcomes. So when you see 70, then all more extreme outcomes are H bigger than or equal to 70, and also the other tail, H less than or equal to 30. And if you calculate all of these probabilities using the binom dist, you get 2.2 times 3.9 e to the minus 5, which is about 8 e to the minus 5. That is 4 zeros followed by 8 in the decimal place. This is a very, very small probability, and this means that the chances of this happening are very low. So if you have 70 heads, probably it's not true that the coin is fair. The coin must be biased to produce so many heads. So low p-values are strong evidence against the null hypothesis of fairness. F statistic for the regression is 40.6. How it is calculated, we don't worry about, we don't care about. The significance is a 5 e to the minus 6, which means 6 zeros or 5 zeros followed by 5. So it's very, very low, which means that now the F is at, what does F mean? It's a test of the null hypothesis that A equals 0 or B equals 0, which means that there is no relationship between C and H. So if that was true, if there was no relationship, then the chances of getting what you saw, namely A equals 4.21 and B equals 0.78, these would be extremely, extremely low. And that means that the inference is that we can reject the null hypothesis that A equals 0 or B equals 0. And so we can reject the idea that there is no relationship. So this inference is correct, even though the reasoning and the logic for this and the p-values, these are all meaningless because they are based on completely wrong assumptions.